A 99% of life's history ended in a single day. The reign of the dinosaurs was Earth's longest chapter. Their 165 million years show profound ecological resilience. But even giants are vulnerable to rapid planetary change. Now that we understand X, let's explore why the catastrophe. The immediate aftermath was not fire, but pervasive darkness. An atmospheric dust blocked sunlight, collapsing the global food web. But this wasn't just starvation, it was a system failure. The KPG boundary marks the abrupt termination point for many lineages. So survival favored the small, the adaptable, and the hidden. The survivors inherited a world stripped bare of giants. But deep ocean ecosystems, buffered from surface shock, endured better. Recovery took millions of years, driven by fundamental chemistry. Fourth, the key to persistence lies in ecological redundancy. But now that we understand planetary shock, let's examine modern parallels. The mass extinction event was driven by atmospheric disruption. Today, we engineer atmospheric changes on a rapid, global scale. The sheer scale of our emissions mirrors prehistoric shockwaves. But ocean acidification threatens modern marine calcifiers, much like ancient life. These tiny organisms form the base of complex ocean food chains. The dinosaurs' fate shows that resilience has limits. A habitat fragmentation destroys redundancy, leaving ecosystems brittle. Large organisms, like large dinosaurs, require massive habitat stability. The largest modern terrestrial animals face similar resource pressures. Decomposition rates, driven by temperature, dictate nutrient recycling speed. Microbes hold the secret to weathering global upheaval. Their ancient chemical balance must be swiftly restored now. Volcanism released massive amounts of atmospheric aerosols, similar to impact. These events reshaped continents and dictated evolutionary pathways. But evolutionary success is often about surviving the pauses, not the peaks. We must learn to value the quiet persistence of small life. Biodiversity is planetary insurance against unpredictable shifts. Monocultures, like massive dinosaur herds, represent high-risk specialization. When one trophic level collapses, the entire structure trembles. Even modern filter feeders are sensitive indicators of water quality. The water availability defined dinosaur ranges, it defines ours still. We are currently testing the planet's capacity for hydrological shock. Underground infrastructure, is the silent bedrock of terrestrial stability. On removing the ancient forests, remove the planet's natural carbon sink. The amber preserves snapshots of ancient atmospheric chemistry. But we analyze these relics to calibrate our climate models precisely. Modern scientists use this deep timeline to forecast future scenarios. The difference between catastrophe and recovery is often a few degrees. The dinosaur world knew extremis ours is creating unprecedented ones. Adaptability requires genetic diversity, the library of life's solutions. But each lost species erases a unique, tested genetic blueprint. The Mesozoic thrived because of its vast, interconnected functional groups. Our modern challenge is to reverse simplification and foster reconnection. Corridors allow movement, preventing isolation and genetic bottlenecks. The dinosaurs teach us that large-scale threats demand large-scale, unified responses. Inertia is the greatest enemy when facing a planetary deadline. Respecting natural timescales informs our urgency in human time. We have the knowledge now, applying it is the final act. This stewardship is the legacy we forge beyond the dinosaurs. Our planet's resilience is immense, but not infinite. The deep past serves as a constant, vital scientific mirror. On every organism, no matter how small, holds critical planetary function. We are part of this timeline, not outside of it. To thrive, we must mimic deep-time ecological robustness. But the lessons of the dinosaurs remain etched in the earth itself.